Okay, so the stationary waves and standing waves and strings are straightforward. There was only one particular choice. For air columns, okay, we have two choices. So let's look at the two choices. Okay, so in air columns, basically we're going to have a tube open at both ends. So first we look at tube open at both ends. So let me explain to you what this means, tube open at both ends. So in an air column, what we're going to have is, let's say that you're given a tube, okay, and of some length L, and we're going to use a tuning fork in this case, and the vibrations of the tuning fork will produce a particular sound and that sound, as it moves through this wave, okay, as it goes from from the tube to the outside, there'll be a reflection of this wave and it'll produce harmonics, just like it did for the string. Okay, the only difference here is it's that we're using sound waves instead, and you'll hear the sound. You'll hear when you have the harmonics, you'll hear the loud sounds. Okay, so let's understand again the restrictions. In the case of the string, we had to have nodes at the two ends. In the case of a tube open at both ends, okay, we have to have an antinode at the two ends. Okay, we cannot have a node here because there's nothing that's blocking it. Okay, so we are going to have antinode. So if you look at the first harmonic, okay, the picture for the first harmonic here, okay, we'll have an antinode at one end and an antinode at the other end. So this is my picture for the first harmonic. Alright, now once again, if you look at this, this is simply half a wavelength. So my lambda 1 is going to be equal to 2 times L. Okay, and so my frequency is going to be equal to the speed of sound divided by lambda 1, which is 2L. Okay, and you'll see that for the tube that's open at both ends, it follows the same pattern as for the string. Alright, let's do a few cases and it'll become very clear. If I have the second case, the second harmonic, okay, once again I'm restricted to having antinodes at the two ends. So I'll have antinode, node. So once again I go here. Okay, and if you see this is one complete wavelength. So my lambda 2 is equal to L, which happens to be 2L over 2 as opposed to 12 over 1 here. So 12 over 2 my second one, and my second frequency is equal to V over L, which happens to be 2 times F1. This was F1. Okay, so for this the nth harmonic is the same. So lambda n is going to be equal to 2L divided by n, and my nth frequency is going to be simply n times my fundamental frequency. Okay, so in this case you have all the harmonics are present here, the first, the second, and everything. Now let us look at the case of the tube closed at one end. Okay, so it's closed at one end. And if you're given a tube that is closed at one end, okay, so once again, because it's closed, the restriction is that at the closed end you have to have an antinode, and at the open end at the closed end you have to have a node, and at the open end you have an antinode. Okay, so my first harmonic for this one is going to look like this. So antinode at one end, and now I can have a node at the other end. So this is going to be there's going to be a node here, and then there's going to be an antinode. Okay, the length is L. If you look at this picture, however, you see that this is a quarter of a wavelength. Okay, so my wavelength lambda 1 is going to be equal to 4 times L. My frequency, my fundamental frequency here is going to be equal to excuse me, it'll be equal to, what is it, V divided by 4 times L. Okay, so that's my first harmonic. Let's draw the next possible harmonic. Okay, once again, antinode at one end, so antinode, and then this is what, oh no, I think I messed something up. Oh yeah, I did. I went to jumped a couple steps. Okay, so let's start this again. So antinode one end, and then node at the other. So antinode and node. If you look at this happens to be, once again, if this length is L, then the wavelength, okay, is, or rather, if I were to complete this thing, I would end up getting a full wavelength. So this L is 3/4 of a wavelength. So the wavelength is 4L divided by 3. Okay, make sure you understand this. 3/4, the full wavelength would be from from here all the way to the end. So the length itself is 3/4. So L is 3 lambda over 4, 3/4 of the wavelength. So the wavelength is 4L over 3, which happens to be equal, and so now I can write my frequency as V divided by 4L over 3, which happens to be 3V over 4L, which is 3 times F1. So here you see we are skipping the second harmonic. Okay, and what we observe is only odd harmonics are present in this one. So this is the third harmonic. Okay, but it's 3 times the wavelength. So this happens to be the third harmonic. Okay. On the other hand, if you look at the next possibility, okay, once again antinode. Okay, so now here this is what we get, the node, and if you look at this is the length is equal to 5/4 of the wavelength. So the lambda, sorry, this one was lambda 3, so lambda 5 is going to be equal to 4L divided by 5, and so my frequency F5 is going to be V over 4L over 5, which is 5V over 4L, which is equal to 5 times the fundamental frequency. Okay, so here once again all even harmonics are skipped and only odd harmonics are present. Okay, so these are all the things that you need to know. In the next video we'll worry about the Doppler effect, and then that will be the end of all these things. Okay.